Okay, I drove to Shenandoah. It's 7 p.m. Ava's and Mara at home with Andy. Mara could be throwing up. It's traumatic enough to throw up when you're 20 months old, but to throw up with Andy around is very traumatic. He tends to overreact. So I came here to do this to make sure you understand what's going on. So listen and listen good. Put your phones away. Stay awake. And if you've been known to be distracted by a computer screen, take notes on paper. You will need to pause the video to take notes. I'm not going to wait for you to take notes as I talk. So pause as often as you need. You know whose faces I'm picturing in my head when I say these things. So I'm going to very quickly try to explain to you how to calculate the pH of a weak acid. I said yesterday or someday this week that the pH of a 0.05 molar solution of hydrochloric acid is 1.3, while the pH of the same concentration of acetic acid is 3.02. You know, I hope you know, and didn't just copy answers from the internet, that the pH of a solution is found by taking the negative log of the hydronium ion concentration. So that concentration must be different for the two acids we're talking about. And it is. So first of all, hydrochloric acid, or HCl, is what's known as a strong acid. We'll talk about bases later. Acetic acid is known as a weak acid. There is a big difference. A strong acid, or a base, changes completely into the hydroxide or hydrogen ion in a reaction. So when you put it in water, put HCl in water, all of it changes to H plus and Cl minus. While weak acids and bases don't completely split up in water. So when you put acetic acid in water, only some of it splits up. All of HCl splits up, only some of acetic acid splits up. So basically, a strong acid, there's more hydronium ion concentration, which is why you get a lower pH. In other words, it's more acidic. Here are two generic reactions, one for a strong acid and one for a weak acid. You'll notice everything's identical except for the arrows here. This arrow at the top reaction, I don't know if you can see my cursor, but I'm circling it. The top arrow, notice how it goes only one direction. That means all of these reactants change into products. Now in the bottom one, sorry, my arrow is a little off, but it's a double arrow. That means not all of these reactants turned into some of these products, but weak acids in water reach equilibrium. We just did a whole unit on equilibrium. I hope you remember some of it. All right. So once again, strong acids don't reach equilibrium. Weak acids do. So once again, a weak substance will only partially dissociate or separate, and will do so until the reaction reaches equilibrium. Okay. Now we're going to talk about Kas and Kbs. They are the same as KEQs or KCs. All right. Only a Ka is for an acid when it's in water, and a Kb is for a base when it's in water. All right. So basically, these values, the Ka and the Kb, represent the relationship between the concentration of the products over the concentration of the reactants when equilibrium is reached. You already know that. Here's a generic reaction. If I tell you to write the equilibrium expression, I hope you would write y to the c times z to the d divided by w to the a times x to the b. The brackets represent concentration, remember, okay? Now, the only reason we change the subscript to A is because we're talking about an acid. Nothing more dramatic than that, all right? So here's that generic acid reaction. I can ignore water. I hope you know why. It's a liquid. It doesn't have a concentration, all right? So if I have HA and I put it in water, it's going to separate into the hydrogen ion and the conjugate base, right? So the Ka is going to be the products divided by the reactant. Sorry, my reactant's a little off again. All right, so Ka is just the hydrogen ion concentration times A minus divided by the concentration of the acid. Okay, now H plus is the same as H3O plus. Remember that. H plus, the concentration of H plus is the same as the concentration of H3O plus. So here is a reaction for a real acid. This is formic acid, I think. I have no idea where this thing went here, but it's right here, down at the bottom. You don't need to say water, we can ignore. All right, so here's formic acid. Okay, it's an acid, so it's going to donate an H. You should know that. Okay, so here it is. Here's the reactant, HCOOH. We put it in water. We can ignore water because it's it's a liquid, and it changes into H plus and HCOO minus. Okay, notice the arrow goes both ways. All right, that's because it's a weak acid and it's going to reach equilibrium. So if we wrote the Ka expression or the equilibrium expression for this reaction, here's what it would be. I have no idea what this line underneath the plus is. It's because I uploaded this to Google Drive. Anyway, you can see that the hydrogen ion concentration times the conjugate base concentration divided by the acid concentration is the Ka. Now, you should see where we're kind of going here. When we talked about equilibrium, the main thing we learned about was ICE tables, all right? Remember, ICE tables stand for initial, change, and equilibrium concentrations, all right? All of them are in molarity. So here is an ICE table, okay? Picture your arrow right here along this middle line, okay? We are going to solve a problem. Okay, and I hope you're seeing where we're going. Where are we going with this? Remember, we want to know how to calculate the pH of a weak acid. Have I said that yet? That's our goal. How do you calculate the pH of a weak acid? For a strong acid, you just take the negative log of its concentration. For a weak acid, you can't do that because not all of the acid changes into hydronium ions, okay? So it says a student prepares a solution for a 0.1 molar formic acid and has found its pH at equilibrium to be 2.38. They want you to figure out the Ka, all right? So, okay, I lied to you. I'm giving you pH on this one. We're going to determine Ka. In another one, I could give you Ka and you could determine pH, all right? So let's solve for Ka. It's a little bit easier anyway. So your ICE table. There it was. It'll be on the next slide too. All right, so our initial concentration of formic acid is 0.1. That's at the very beginning, okay? And that's your initial concentration. How much products have we made? None. Okay, so here it is. Just like we did in the last unit. Remember, the arrow's right here on this middle line. They didn't draw the arrow, okay? Now, what's going to be the change for your reactant? Okay, the acid, when you put it in the water, its concentration should go down. Okay, so it's going to be minus X. I thought that was on the next slide, but it's not. Minus X. The concentrations of your products will go up, so they're going to be plus X's, right? Okay, so here they are. If you need to take notes on the slide before this, that's just what we learned in equilibrium. So you can go back and hit pause and do that. So you should know that the equilibrium concentration for the reactant or the HCOOH will be 0.1 minus X. And the other two equilibrium concentrations will be X's, correct? All right, here we go. Beautiful, right? Now, we need to know something in our box to be able to solve for Ka, all right? If you've written hopefully you know how to write the Ka expression, all right? Now, so we have pH. Remember, pH is the negative log of the hydronium ion concentration. Now, notice how they just put H plus in for that. That is completely fine. Remember earlier I said H plus is H3O plus. Their concentrations are always the same. I have no idea what dolphins in San Fran mean, but if you Google it, I bet you'll figure it out. Anyway, if we can solve for X, we can solve for Ka. All right? We can solve for X because in our reaction, if you look back at it,